welcome to the podcast of Transport Phenomena hosted by me, Tushar and Khant. In this podcast, we are going to solve various problems based on thermal conductivity estimation.
But before we begin discussing about the problems, let's first take a quick look at the basics. So, thermal conductivity is represented as the property that tells us how efficiently a material conducts the heat. Now, do you know, Tushar, in gases, heat transfer primarily happens through molecular collisions. So, the factors like molecular diameter, molecular interactions become very important.
Exactly. Now estimating thermal conductivity for a pure gas is relatively straightforward. But when we deal with the gases of complex mixture, things get more complex. You can't just straightforward averages the value. Instead, we use semi-empirical formula and that consider mole fraction and individual gas properties and molecular weights.
These formulas aren't just textbook stuff, they are also applicable in real life engineering. Like for example, if an engineer wants to design a combustion chamber, they need to accurately calculate the thermal conductivity of the flowing gases, as if the value is off the limits or even if the value are higher than expected values, then the whole system could either fail or overheat.
Even I remember a classic example of industry. In an ammonia synthesis reactor, there are a mixture of hydrogen and nitrogen gases at high temperature and pressure. If you don't estimate the gas mixture thermal conductivity correctly, the cooling system design could completely fail. And that's why thermal conductivity property estimation is critical in chemical process engineering.
So in this podcast, we are going to discuss the problem set of 7 numericals, in which the numericals are based on the marking system that we see in the exam, like for 3 marks, 4 marks and 5 marks equivalent. So you may get an estimated idea of how you are going to face the challenge in exam. The questions involve the covering portion of mole fractions, I guess, then mixing of gaseous mixtures, then molecular diameters and those values it is covering. Also, it will focus on the handling of data and converting of data, which also you have to keep in mind.
So Khant and I will be solving the problem, and each of the problem is designed to help you practice step-by-step application of concept without diving into unnecessary theory.
And one more thing, if you want to score good marks in transport phenomena exam, then this problem structures and its relevant theory is a must know. So you will feel confident after practicing these problems.
Alright then, before starting the problem, let's understand all the basics and formulas of estimating the. Firstly, we will discuss methods for estimating the thermal conductivity. As we know, thermal conductivity is a measure of material's ability to conduct heat. It is denoted by symbol K. Its units in SI is watt per meter Kelvin. Its CGS unit is calorie per centimeter second degree Celsius. Its British unit is BTU per hour feet Fahrenheit. Now we will discuss the method of estimating thermal conductivity. So thermal conductivity using the viscosity for gas. K is equal to Cp mu by PR, where Cp is heat capacity at constant pressure, mu is viscosity, PR is Prandtl number. We use this formula when Prandtl number is given. It is only for gases. Another method is Chapman-Inslog formula. It is a experimentally determined formula. It is K equal to 1.9891 into 10 to the power minus 4 into under root T/m into sigma square omega K, where m is molar mean molecular weight, unit is mass per mole, sigma is collision diameter, it is represented by L, and unit is angstrom. Omega K is collision integral for thermal conductivity. It is determined by the Lennard-Jones table. We will solve in numerical further. We can see that the unit obtained from this formula is calorie per centimeter second Kelvin for thermal conductivity. The temperature we will use in Kelvin, and Sigma is angstrom. Third formula is Euchen relationship. For monoatomic gases, K equal to 15 by 4 RYM into mu. For polyatomic gases, K equal to Cp plus 5 by 4 into RYM into mu, where R is universal gas constant, Cp is specific heat capacity. For monoatomic gases and polyatomic gases, we have different formulas, so we will use accordingly by the nature of gas. It is monothermic, monoatomic or polyatomic. So the fourth method is thermal conductivity for gaseous mixture. When we are dealing with mixture of gases, things get bit more complex. Here we use semi-empirical formula mixing rules to estimate overall thermal conductivity. The formula goes something like this: K mixture equal to alpha equal to 1 to n x alpha into K alpha upon sigma from beta equal to n x beta into phi alpha beta, where yi where x beta equal to the mole fraction of the component I. Ki is the thermal conductivity of the pure component. Phi alpha beta is interaction parameter between component I and J. It is a coefficient constant. Phi alpha beta is 1 upon under root 8 into 1 plus m alpha upon m beta to the power minus half into 1 plus k alpha upon k beta to the power half into m beta upon m alpha to the power 1 by 4 to overall whole square, where m alpha or m beta is the molecular mass of that component. This formula is very useful for systems like air hydrogen or methane nitrogen mixtures where individual conductivities are known. As we know, while gases are most commonly estimated using these equations, as I discussed earlier, for solid and liquids, the thermal conductivity usually comes from experimental data or correlation based on structure. Like for metallic solid, it's very high conductivity. For non-metals and porous solid, it is generally low conductivity. For crystalline material, which is you called as ordered structure, or basis amorphous material, which is you called as disordered material, the different behavior with temperature. For metal, temperature with the rise of temperature, conductivity or thermal conductivity of material decreases. For non-metal, on increasing the temperature, thermal conductivity also increases. For the estimation of thermal conductivity of solid, we have the one equation which is called as Weiderman-Franz-Lorentz equation, which is like K upon Ke into T equal to L equal to constant, where L is the Lorentz number. The Lorentz number is L is about 22 to 29 into 10 to the power 9 volt per Kelvin square for pure metals at 0 degree Celsius. For above 0 degree Celsius, increases of 10 to 20% per 1000 degree Celsius. For estimation of thermal conductivity of composite solid, we have two formulas. For small volume fraction of phi, the Maxwell gives the relation K effective upon K naught equal to 1 plus 3 phi upon K plus 2 K naught upon K1 minus K naught minus phi. It is for small volume fraction of phi. Or for the large volume fraction phi, the Rayleigh gives the expression K effective upon K 1 plus 3 phi upon K plus K1 plus 2 K naught upon K1 minus K naught minus phi plus 1.569 into K1 minus K naught upon 3 K1 minus 4 K naught into phi to the power 10 by 3. We have given a problem statement. It states that estimate the thermal conductivity of gas mixture with the help of information given below. In this question, we have to calculate thermal conductivity for the gaseous mixture using the data of the individual species with thermal conductivity and the viscosities. We have given the species CO2, O2 and N2, and their respective molar fraction is given 0.33 for CO2, 0.33 for O2, 0.33 for N2. And thermal conductivity in calorie per centimeter second Kelvin is also given 383 for CO2, 612 for O2, 627 for N2. And viscosity data is given in gram per centimeter second. In 14624 for CO2, 2031 for O2, 175 for N2. Now we will learn how we will tackle this problem. This type of problem that contains various species and individual data of that given, and how can we tackle this. Okay. So in this question we will use semi-empirical formula to calculate effective thermal conductivity of the mixture accounting for interaction between different gases. We will use semi-empirical formula. The semi-empirical formula for calculating thermal conductivity for gaseous mixture is given as K mixture equal to sigma alpha equal to 1 to n x alpha into K alpha upon sigma from starting from beta to the nth species x beta into phi alpha b. And the meaning of this term is the x alpha is mole fraction, K alpha thermal conductivity of the pure chemical species. The thermal conductivity of the pure chemical species is K alpha. And that term, the new term phi alpha beta, what is that? That is the coefficient, and the expression for that coefficient is phi alpha beta. Phi alpha beta, that is, we will calculate one species related to the another species, so it's written as phi alpha beta. It's equal to 1 upon under root 8 into 1 plus m alpha upon m beta to the power minus half into bracket 1 plus k alpha upon k beta to the power half into m beta upon m alpha to the power 1 by 4 to the whole square. So we will calculate the phi alpha beta from that formula, and we will put into that equation, and we will calculate the thermal conductivity for the overall mixture. Proceeding further in the question, we will need the molecular weight of the species. So we have written the molecular weight of the given species. For CO2 44.01, for O2 32, for N2 the molecular weight is 28.016. So we have extracted all the data, and now we have created a table that contains alpha, beta, m alpha by m beta, k alpha by k beta, phi ab, and sigma x alpha into x beta. So for the calculation of phi alpha beta, for CO2 we have taken alpha equal to CO2, beta equal to CO2 because we have to calculate for the three cases. CO2, first we will take CO2 with CO2, we will take CO2 with O2, and CO2 with N2 is beta. So the calculation is m alpha by m beta equal to 1, k alpha by k beta for CO2 as CO2 equal to 1. And now we will put all the details into this formula. And now we are substituting the values, because 1 plus all values are 1. Then substituting into the formula, we will get phi alpha for CO2 is 1. Similarly, now we will take beta equal to O2. M alpha upon m beta is 1.375, k alpha upon k beta equal to 1.6258. Again we are substituting into the formula of phi alpha CO2 into CO2 and O2. Now substituting all values into the formula, we will get phi CO2 and O2 is 0.68697. Again, now we will take beta as n2, and the date m beta upon m alpha equal to 1.5709, k alpha upon k beta equal to 1.6108. Again, substituting all value in the formula, we will getting phi CO2 N2 equal to 0.6358. Since we have obtained all the phi AB values for CO2, now we can calculate sigma beta equal to 1 to 3 x beta into phi alpha beta, and we know that we have given mole fraction for all the species. Now we will put into that expression and we will calculate x alpha into phi b. 0.33 into 1 plus 0.33 into 68697 plus 0.63 into 635758. We have obtained x beta into sigma beta equal to 1 to 3 x beta into phi AB for CO2 to all CO2 with respect to all species. Now similarly we can calculate for O2 and N2 and make a table of that. For O2, the phi O2 to CO2 phi AB value is 1.5097, O2 to O2 1, O2 to N2 0.9238, and sigma value is 1.13308, and the value for N2 CO2, the phi alpha beta 1.6351, N2 and O2 1.081, and N2 and N2 1, and the sigma value is 1.2263. Now we have obtained all the details. We can put into the formula. The formula is k mixture equal to alpha equal to 1 to n x alpha k into k alpha upon sigma beta equal to 1 to 3 x beta into phi alpha beta. Now we will put all the values into this. The x alpha for CO2 is 0.33. The k alpha is given as 383 into 10 to the power minus 7, and the sigma value we have calculated here, so we will put into this. And for O2, 0.33 is the mole fraction. The thermal conductivity value is from the table is 612 into 10 to the power minus 7, and sigma value is 1.133 plus for the N2, the mole fraction for N2 is 0.33 as well, and the thermal conductivity of N2 is 627 into 10 to the power minus 7, and the sigma value is 1.2263. We have calculated the expression. It's coming 5.118 into 10 to the power minus 5 calorie per centimeter second. We can write as per the question. The thermal conductivity of the mixture is 511.86 into 10 to the minus 7 calorie per centimeter per second Kelvin. Hence, we have solved this question. In this question, we have given the problem